So I'd like to welcome Kevin Scannell today from St. Louis University in the United States. And Kevin Scannell is a professor of mathematics and computer science at St. Louis University, as I said, where he has taught since 1998. And his main interest is the development of technology that helps speakers of indigenous and minority languages use their language online, with a particular focus on Irish and the other Celtic languages. And today he's going to talk about towards explainable AI for Irish grammatical error correction. So we're delighted to have you here, Kevin, and Lenarijk, Matatu Ri.
Anoa, Gurvagat, Doris. So I'll plow ahead in English, and I'll do my best to not make assumptions about that people know much about Irish, although I know we have some, for sure, some Irish speakers here. So very broadly, let me set the stage and tell you about the problem that I'm interested in working on, and that's the problem of grammatical error correction. So very simple terms, this is a program that takes a sentence as input and then outputs the sentence with any grammatical errors corrected. There are some related problems that you'll see work on. The easier problem of grammatical error detection, which takes the sentence as input and maybe highlights, puts a squiggly line under the errors without necessarily telling you what the correction is. I'm actually interested in the harder problem, which is grammatical error correction plus some explanation as to why that correction is the right one. So this is a problem that's pretty widely studied these days in natural language processing. If you read the latest research, almost all the papers relate to English, which is much like other sub areas of NLP. But there are more and more data sets emerging for training sort of machine learning based systems to solve this problem. For maybe 20 languages, English obviously has the most data, but more and more languages are making an attempt at this problem. One of the challenges is that it's hard to nail down exactly what you mean by a grammatical error or an error. In practice, nobody really tries to do this. The definition of what you mean is effectively defined by the training data sets that people build. So just as an example, some data sets will mark errors for things like incorrect terminology usage, right? Or errors in style, where something might be grammatically correct, but it could be improved in terms of style. These are useful things for people who want to use the software for language learning, for example, but that might not be specifically grammatical errors. This is a very challenging problem. If you look at the state of the art for English, where there's lots of data, relatively speaking, the state of the art scores are in the 60th percentile for F scores. Basically, the issue is that the precision of these systems the recall of these systems is very, very low, which means that there are often errors in a text that these systems just don't detect. So what I'd like to do is I'd like to talk about this problem for Irish, where in a lot of ways it's easier because the most common grammatical errors tend to be easier to find and trap than they are in English. So just by nature of the language we're looking at, the scores we're able to achieve will be much higher than for English. So I'm going to focus on a subset of grammatical errors, and these are the errors that relate to initial mutations in Irish. So initial mutations are a phenomenon across all the Celtic languages. And again, for many of you, this is familiar, but they're basically changes to the spelling or the pronunciation of a word at the beginning of a word that are triggered by some kind of grammatical context. So a simple example, a sailboat is a bod shoal, but if I say my sailboat, it changes the pronunciation and the spelling of bod to wad, BH. And if I say our sailboat, it's yet another change to our mod shoal. There are lots of contexts in which this happens. Some of them relate to gender, say far for man. then I want to say the poor man, it's een verbocht. But if I want to say the poor woman, it's een van wocht. So both the word for woman and the word for poor undergo a change here, and that's related to the gender. Other contexts, in the dative case, if I say on the sailboat, there is a change to boat again, which interestingly varies across dialects. And I'll come back and talk about this a little bit, but this is a important marker of some dialects of Irish versus others. And just as another example, there's a mutation that occurs in the genitive plural, for example. So if I say the men's toilet, it's the toilet of the men, then the word far for man gets this mutation, which in the writing system is a prefixed BH. So the rules around these are very complicated, and for learners, they can be challenging. For native speakers, maybe not so much, but for learners of the language, these are, outside of spelling errors, the most common errors that people make when writing Irish. Now, what are the rules? Well, there is an official standard. In fact, there are multiple official standards. So the first version of the official standard was published in the 50s. It was recently revised and then revised again, 2012 and 2017. So the 2017 version, I guess, is the most up-to-date official standard. Among all of the other things that are laid out in the standard, it has rules for specifying when the various mutations in Irish should be applied. There are some challenges. So even if you intend to follow the official standard, the first and biggest challenge is that the official standard does not align completely with existing learning materials, grammar books. Even the standard dictionaries of Irish don't exactly match up with the official standard as it's published. Fine. The standard is viewed by some as artificial in the sense that no one completely adheres to the standard in the way that they speak. Almost everyone will speak some dialect of Irish, and typically the dialects will have variations from the standard in the way people speak and write. Even if you accept this and say, all right, well, we're going to target in our grammar checker, we're going to target the published standard in 2017, it's still not completely trivial. And part of the reason is that some of the rules as they're written there's some interpretation and some wiggle room as to how to correctly apply them. And what this means is that even writers who are committed to following the standard, say translators who are translating official documents, don't always use the rules in exactly the same way, exactly because of this kind of wiggle room. What this means for us in terms of trying to use machine learning to train a system to do this is that there's essentially no completely reliable training data. You can collect text where people are trying to follow the standard, but there's always going to be a little bit of variation. If you try and collect a bigger corpus, which is kind of people's natural writing that they use online, then there's quite a bit of variation from the official standard. So let me give one example, and this is probably rhetorically not a very good example, but it's kind of fun to talk about. And this is most effective if I can actually incite some argument among the Irish speakers on the call. So should it be Saoirse Cainse is freedom of speech? Should it be Saoirse Cainse or Saoirse Cainse? Well, we could take a vote, I suppose, but instead of voting now, what I did is I collected 100-something million words of Irish from the web and just counted. So this is a little bit simplistic, but 177 million words of Irish. There were 687 instances where the second word was not mutated, and just 28 where it was. So if we believe in democracy in terms of the standard, then it appears that we shouldn't mutate in this context. I also looked at Similar example for freedom of religion, Saoirse Creidimh, or it could be Saoirse Chreidimh. And there it's less common, but there are 100-something examples, 85 without the mutation and 26 with the mutation. So sort of a closer call there in some sense statistically, but still it seems to be in favor of not mutating. The issue is that if you look in standard dictionaries, it's sort of a mixed bag. So the screenshots on the left are from the FGB, the standard Irish English dictionary, still standard Irish dictionary from 1977. So freedom of religion there, it does have the mutation on religion, but freedom of speech, it does not, Saoirse Caiinte. If you look in the new English Irish dictionary, which is online, under freedom, we have a couple instances where that second word is mutated, but then sort of deeper in another entry, there's an example where freedom of speech is not mutated. And so the point that I'm making is that there is, even for those who are attempting to stick to the standard, some very natural variation that occurs. The other thing that this brings up, of course, is whether any of this really matters. You will be completely understood as a speaker of Irish, whether you include this mutation or not. Certainly, if you include it or leave it out in writing, nobody's going to be confused by this. This is the sense in which this is maybe a suboptimal example to show you, but I at least wanted to exhibit some standard references in the language where there seems to be disagreement about what the right mutation is. So a little bit of history. I've been thinking about this problem for a long time. My first attempt at creating a system that could detect grammatical errors was rule-based. I did this kind of early days for me as a learner of the language and somebody working on software in the language. And it was based on explicit rules. So the rules are very complicated, and I did my best to sort of encode those rules in a machine-readable form. It was based on a simple part of speech tagger, and then applying pattern matching to the part of speech tagged text. So you could say things like, if I have a feminine noun in the nominative case, and there's an adjective following it, then that adjective should be mutated, except for maybe some exceptions. The exceptions and then exceptions to the exceptions and so on makes the rule set extremely complicated. In the current version, there's over 2,800 rules. Fine. Good news about a rule-based system is that it's possible to provide explanations and a diagnosis when an error is flagged, because you know exactly which which rule has been broken, and you can report that to the user. So this is one of the big advantages, and really why I approached it this way to start. But there's lots of negatives. Rule-based systems are kind of known to be brittle in the sense that if you have out of vocabulary words or anything that varies from the formal way that the rule is written, then it's going to make mistakes. Of course, it's tedious to implement all of these rules. You could say, well, that work is done, but it's also really tedious and difficult to maintain them because they're so complicated with exceptions to exceptions. When somebody reports an error, I have to figure out how to fix it. It can be exceptionally difficult. The biggest issue with the rule-based system is that not all rules are encodable using the formalism that I laid out for rules. In particular, if you are expressing rules in a part of speech tagged stream of data, that part of speech information allows you to capture a lot of things, but not everything. So there are some rules that depend on syntactic information, for example, which would not be incorporated into a part of speech tagged corpus. And then similarly, some semantic information that without a semantic tagger, for example, would be impossible to encode. For years after that, I looked at approaches to doing this in a machine learning unsupervised way, which is to say that you have lots of text in Irish that you can collect from the web. Those exhibit the actual usage of these mutations by Irish speakers. Why not learn how to do this in that way? Now, of course, by doing this, you're sacrificing any hope at getting explanations. All you can say is this example looks like it should have a mutation, and the explanation is, well, because that's statistically what happens most often on the web. But nevertheless, I think it was an interesting way of looking at this. What I did was formulate it as a tagging problem. So laid out 5 tags. So one of the tags, the N tag, is no mutation. And then the other tags are various kinds of mutations in Irish, shebu, uru, prefix T, and a prefix H. The good news about this approach is that in Irish, you can remove the mutations algorithmically, at least almost, which is to say that in context, I can take a word and recognize whether it is a shebu mutation, for example, and then remove that mutation and then use that as training data. The almost is because of the prefix H. There are sort of edge cases where you have an H at the beginning of a word and you don't know whether it's part of one of the rare words in Irish that starts with H or whether it's actually a prefix H. In Scottish Gaelic, they have the good sense to include a hyphen after the H all the time, as we did in Irish in older orthographies, but this is just a small irritation. The state of the art for doing these kind of machine learning approaches in 2004 was to use n-gram models. And I tried very hard for years and got some results on this, but it's too hard, to put it bluntly. Part of the issue is that a lot of times mutations are determined by more than just the words in the surrounding context. They depend on subtle character level information. For example, the ending of a previous word might be slender or broad, and that can affect things. If we're not incorporating, if it's purely unsupervised, we don't have any part of speech information or gender information, that has to be learned also from character level information. So if I see something that ends in EOG in Irish, that looks like a feminine noun to me, for example, that's all information that has to be gleaned at the character level. And combining the word level model together with the character level model in an n-gram context is challenging, to say the least. There are techniques for doing this. There's a technique called parallel backoff or generalized parallel backoff that, again, as everybody moves toward neural network approaches, is kind of fallen out of fashion as maybe just a footnote in NLP now, but you can make some progress, but it's a suboptimal approach in the long run. So amazingly, it turns out that you can, with neural networks, solve all of the problems from the previous slide, incorporate character level information and word level information into a single model, and train an unsupervised system with very little difficulty at all. And it turns out that that unsupervised system can achieve very high accuracy in predicting mutations. So this was something after years of tearing my hair out, trying to build n-gram models for doing this, I was able to do essentially in a weekend. So all of the difficulties in terms of smoothing and back off are thrown away. The model that I did, this is now 4 years ago, used LSTM layers and then by LSTM at the character level, which is sort of a standard approach. No back off, no hand selected features, no nothing. The model learns exactly what it needs to learn. And it achieves very high accuracy. Some of the interesting, fun things that it does, it successfully learns features like gender implicitly. That's actually what this picture is here. It's sort of a visualization of the nouns in the word embedding in this model, which shows kind of the masculine and feminine and red and blue clustering near each other. And you can even have out of vocabulary words. I like this example, schnidog, that I made up. It's a completely made up word, but if you pass this to the model, it effectively will recognize that that it looks like a feminine noun. And then even at the word level, some really subtle kind of victories of this model. For example, I've given it sentences where there's a dialect choice between two possible mutations, and it appears to make the right choice, for example, for the Ulster dialect, based on sort of semantic contextual clues. One example would be a surname that is sort of most common in that dialect. I believe is the signal that it's using to detect that that one particular mutation is the right one over another. Okay, so this is work I've actually talked about, I think, in this same seminar 4 years ago when I was in Ireland. So I won't go into detail on it. I do want to say one thing for those who haven't heard me talk about this before. One of the things that falls out of this work is that you can get an estimate of the information content of the mutation system in Irish. So an empirical estimate. So this is, again, a 5-fold class tagging problem. So there are 5 possible tags. And effectively, we're trying to minimize the cross entropy of the model. So you want to have the best possible predictions of these tags. And the end result is that the best model we train gets entropy, which is very, very close to 0. And if you measure this with kind of log base 2 and the cross entropy, you get units of bits. And the best model that I trained has an entropy less than 0.07 bits per word, which is to say, this is, again, an estimate and I guess an upper bound on the actual information content in bits per word of the mutation system. So the fact that this is close to 0 informally says, quote unquote, that Irish initial mutations carry essentially no information. And this is sort of an empirical proof of that fact. The number is actually even lower than 0.07 because when I estimated this number with a test set, the places where the model made incorrect predictions, the model was actually correct and the test set was wrong. So mistakes were people writing the corpus texts actually made mistakes. So this is in fact even closer to 0. The very small remaining bits of information are standard things that people know about, like third-person possessives. The mutations are often a strong signal as to whether it's his or her or their. That's sort of a well-known example. But what's interesting to me is that there are many things where I think teachers of the language say that the initial mutation is a strong signal for one thing or another, where it's not really the case. So for example, in Irish, we have direct versus indirect relatives, which are in the grammar books primarily distinguished by whether they have a lenition or eclipsis mutation. In fact, it's essentially trivial, or at least for this neural network model, to distinguish the two without having access to that mutation. All right. So again, I'm going to critique my own work and tell you the reasons that while this is interesting, it's not very useful. First of all, of course, it's completely unsupervised. It's learning mutations as they're used by the language community, which we've observed is different from the official standard. As is well known with neural network models, it can sometimes make mistakes that are inexplicable and very difficult to debug because you're not really sure what's happening with the weights behind the scenes. Most importantly to me, maybe second most importantly, in terms of being useful for learners of the language and writers in the language, when you train a neural network and you're trying to minimize some loss function, it's going to minimize that loss function. And in this case, what it does is it can get very high accuracy because there are lots of very easy cases for this problem. And it's very good at the easy cases. And when you look at the cases that humans find challenging and difficult, the neural network finds those difficult as well. So a grammar checker that that only reports errors on the things that mistakes that humans don't make anyway is not all that useful. But the number one critique of this, of course, is that just by the nature of the way it's trained, there are no explanations. All the system does is when you give it a sentence, we'll flag a word and say, this should have the Shevu mutation, for example, with no explanation as to why. And that makes it, it's not completely useless, I think. I think for a fluent speaker or somebody who knows the standard very well, it will catch your just silly mistakes. It's more like a spell checker in that sense, where you, if you see the reported error, you say, oh, of course, I should have had a Shevu there. But for a learner, this makes no sense at all. So really the point of what I'm talking about today is how do we take the same approach to train a neural network in an ideally unsupervised way, but retain the ability to give the user explanations as to why an error is being reported. So the setup is as follows. We're going to continue thinking of this as a tagging problem, but instead of just 5 tags, I'm going to have dozens and dozens and dozens of tags. So each tag is then augmented with a reference to a particular section of the official standard. The 2017 standard has numbered sections. So the little screenshot at the bottom from the standard. Every tag is going to be augmented with a number referring to the section of the official standard that explains that mutation. Fine, that's the setup. Now, by changing the tag set like this, it's no longer something that we can do in a completely unsupervised way. Because again, we can recognize that Van in this first example right here has Shevu, and in the previous neural network that it should be tagged S. But there is no unsupervised way yet of recognizing that it's Shevu with this explanation as to why that mutation is there. So this becomes a challenge. How do we produce millions of training examples that will allow us to reproduce the neural network approach that we just did? And it turns out that the answer was kind of sitting in front of me all along, and that is that we have this incredible resource, the Universal Dependencies corpus that was originally created by Teresa Lin as part of her PhD work, that does analysis of iris sentences and does all of the things that we need to make good predictions of mutations. So if you don't know much about universal dependencies, it's well, the Universal Dependencies project creates corpora, which are dependency parsed sentences. A dependency parse is what you see here on the screen. We have the sentence together with well, part of speech tags, of course, but then every word is connected to its dependence. All right, so the arrow points from a word to its dependence, or if you want to follow the arrows backward, they point words to their heads, their syntactic heads. Every arrow is labeled with a syntactic role as well. So the root word here is the root verb of the sentence, and then there's a dependent which refers to the subject, the nominal subject of that verb. This determiner is a dependent of the nominal subject, and so on. All right. So those corpora can be used to then train dependency parsers and taggers for Irish. The good news is this is sort of a pan-Celtic thing. So Teresa's work kind of kicked off an effort to produce tree banks in the same formalism for the other Celtic languages as well. So Colin Batchelor has a tree bank for Scottish Gaelic. I produced one in 2020 for Manx Gaelic. And then there are tree banks for Welsh and Breton as well. Cornish is the one Celtic language that has yet to produce a tree bank. We put some effort across the Celtic languages into sort of harmonizing the annotation schemes. This is the universal and universal dependencies. There's hope that the various language groups will work together to have these annotations make sense cross-linguistically is essentially the point. We've made some effort. There's some places where I think we disagree from language to language over the right way to do things, but we're getting closer to something that's uniform. So if you've never seen it, this is what a typical file looks like. It's essentially the same information as was on that previous slide, except there are some additional columns here. So the various tokens, it's one token per row. This is the surface token. This column is the lemma. This is the part of speech. These are grammatical features, and I'm sure they make sense more or less. You have this is a verb which has a mood and a tense. The form marks that it's actually lenited. It tells you what the mutation is, which is relevant for us. This pronoun is feminine, singular, third person, and so on. This column points to the head with reference to these numbers. And then this is the syntactic role of each word. All right. So one of the things that I did in working on this tree bank was to, first of all, correct errors that were in the tree bank. The features in particular were particularly challenging. Those features in the first version that they appeared were not fully hand checked, and that meant that a tremendous amount of work had to be done in order to essentially correct the errors that were there and bring them up to sort of gold standard. And the way that I did that is I developed a suite of tools that went through the tree bank and looked for errors in the feature values. All right. So that code is all open source. This repository right here is kind of what drives everything that I'm talking about today. The goal of this repository was to actually be cross-linguistic across at least the Gaelic languages, because again, I wanted to apply these same QA tools to the Manx and Scottish Gaelic tree banks. The way it's implemented is it's essentially rule-based. It's constraint-based. So we start with a parse, a dependency parse. So like the tree that I showed you earlier, that parse might not be completely correct, but we take it at face value, and then that parse implements constraints on what the possible feature values can be. So as a simple example, we can formulate rules like the rules for initial mutations using this formalism. So if a noun is feminine and it's preceded by a definite article, and there's a dependency relation that says that that definite article is a dependent of the noun, and so on and so forth, and it doesn't meet various exceptions, then that noun should be mutated, say. So given the context, given the dependency parse and the relations and the feature values of surrounding words, we should be able to make correct predictions of every feature value for every token. We're not quite there, but it's probably in the high 90s, or 98 or 99% of the feature values can be accurately predicted. In our context, where we're just interested in predicting initial mutations, what we really care about is predicting that form feature correctly. So the form, anytime a word is mutated, that form feature appears and it tells you exactly what the mutation is. So what I did was I originally was aiming at trying to improve the tree bank and doing QA. But what I recognized was that the suite of QA tools could be used to produce exactly the kind of training data that we need. And the first thing that I did was I rewrote the code so that it effectively completely parallels the rules in the printed official standard of Irish. So I took a little screenshot here on the left. You see a snippet of this code from that Grammatical repository, and on the right you'll see a little section of official standard. This is sort of a notorious section of exceptions to the rule that a noun in the genitive case after a feminine noun gets a mutation. So there are tons of exceptions, I guess 13 exceptions to this. And they're all implemented in code. And what this means is that given the context, given the dependency relations, I can more or less accurately tell you whether a noun should have any particular mutation. A little side benefit of this is, without doing any machine learning, if you decide you want to trust this Grammatical repository and this effectively rule-based system, which of course depends on the dependency parser, this allows you to do a corpus-based analysis of what the most common errors are. What I'm showing here is not really a display of the most common errors, but what it's showing is the rules or the sections of the official standard that people break most often. This, I think, is useful in two different ways, of course. The first being that these are the places where learners of the language are making mistakes, where it could potentially inform teachers of the language as to what are the things that prove most challenging. But I also think it's potentially useful in any revision of the official standard, in that some of these rules are purely just dialect issues. So there are ways that people in writing very natural Irish diverge from the standard. So this one here, sort of toward the bottom, Don Villa is sort of probably the way I would say it, sort of to the poet, as this eclipsis mutation. Formally speaking, that is against what the standard says, which says that should always be a lenition mutation. And almost certainly the 6% of sort of variations from that standard behavior are all just people writing very natural Irish. So in any case, this is not really what I wanted to talk about, but it's a nice side benefit from just the existence of that Grammatical code. And I'm unaware of any kind of corpus level survey of errors of this kind. Okay, so what is the solution to how do we produce the training data that we need to redo our neural network model? We use the code that I just described. So take a large corpus of Irish, 100 million words, say, run it through the dependency parser, which is trained on Teresa's treebank. And then this is an important step. The parsers that come out of the dependency parser are not perfect. I think the F scores are 80s, between 80 and 90%. It's going to make mistakes. Often the mistakes that it makes don't impact the predictions of mutations and so on, but you do have to be a little bit careful. So what I do is I throw away the tokens where the QA scripts predict a feature value which differs from what actually comes out in the tree bank. Now, these occur for a couple different reasons. One is that the parser made a mistake, and therefore, since the parse is incorrect, the QA scripts make the wrong prediction of what the mutation should be. But it also picks out and throws out examples where the corpus itself is just not compliant with the standard, either through a user making an error or somebody writing in a dialect form that's not compliant with the standard. If we want to train a system that is compliant with the standard, if that's the choice that you make, then this step allows us to do that more effectively. So the remaining tokens are attached through these QA scripts to some constraints, right? So one or more constraints. And then the trick is to create synthetic training data by intentionally violating those constraints. So for example, this is a sentence straight from the standard, printed standard. The woman is singing, Van Akana. The constraint that comes out of that sentence is the one that I showed on the earlier slide, that then requires the shevu, this monition tag, together with a reference to the section of the standard that explains it, that a feminine noun after a definite article gets this. And then we intentionally violate that constraint. And of course, there are two ways of doing that. You could remove the mutation completely, which would give you an incorrect sentence, or you could add the incorrect mutation, which would also be completely wrong, and probably a rarer error. But in either case, those are both mistakes. And now we have training examples that say, if somebody were to type this, that is the tag that should be attached to ban or man. Fine, that is the training data. I can effectively treat this in an unsupervised way. Now, of course, it has dependencies. It's depending on Thesis tree bank and the parser that comes out of that. It's depending on the accuracy of my QA scripts. But setting those aside, I'm able to produce effectively unlimited amounts of training data through this approach. And once you have hundreds of millions of words of training data, you can train a neural network to predict these tags accurately. I'm not going to report accuracy numbers, so apologies for that. Because I don't have a large enough test set where I can say, in these 10,000 examples, the accuracy was this, but that is work in progress. So hopefully before long. So what are the benefits of this approach? Just to kind of summarize things. By throwing out the sentences that appear to violate the predictions of the QA scripts, it kind of neatly handles the issue of non-standard texts in the training data. The other big win, I believe, and this is also work in progress, is when I explained how the easy things are easy and the hard things are hard. This approach gives us a way of effectively getting around that issue by oversampling these rare contexts where most of the errors occur. So we can just upsample the number of places where, I don't know, the rules for mutations after prepositions like gone and words like that are very common errors that people make. All we do is upsample those in order to provide the neural network additional examples to make better predictions. The thing that I'm most excited about is that nothing that I said really restricts this to predicting just mutations. It's completely general in the sense that as long as you have the QA scripts that are able to make reasonable predictions about what the feature value should be, then the same approach should be able to, in an unsupervised way, make those same predictions. So for example, there are features around verb tense, there are features for marking agreements, singular, plural adjectives, and so on and so forth. All of those are things that this approach should be able to capture in grammar correction. And then the other nice thing is that because these tree banks exist for the other 4 Celtic languages at least, except in Cornish, the same approach should apply there as well, given that somebody does the work to implement the same QA scripts. I've made a start on Scottish Gaelic and Manx, but if one were to do the same thing for Welsh and Breton, the same approach should work cross-linguistically. And that is all I had, Cardamom.
Ja, Christian Sumul thought I'm willing hashtag Dine, I should say. Is there any question in the room? You can also raise an issue in the chat if you have a question, and I can read it out.
So this is a pathological one, but the famous Budgil Wanya is a milk bottle, whether it contains water or milk, but Budgil Banya is a bottle of milk, whether it's just a water bottle that happens to have milk in it. I was wondering, could you give it sentences where semantically the meaning is humanly obvious, like Hugshi do budil Banya the whole. So that's a bottle of milk. And or vi ushke, or ushke vi, no, I'm trying to think trying to avoid it, but something like vi ushke se would you'll want. So would you'll want, yeah. Anyway,
yeah, it's tricky. It's tricky to make mistakes. No, this is one of the very subtle points. So,
would your neural network model be clever enough to pick those up? I would guess not.
You might be surprised. So I don't have numbers that I can report, but these are the sorts of examples precisely that I had in mind with trying to do an unsupervised approach. So I haven't looked at examples precisely like that. This would be a question even for the previous model that exists. So this is actually an experiment that I could do. But I mentioned the Obuil example, which was similar in the sense that it was making the correct prediction from something that it's learning about the semantics of the sentence purely. So I am not sure, but this is the reason that I think an unsupervised approach that uses neural networks, that uses word embeddings and so on and so forth, has some hope of actually solving problems like this. Even though the kind of information content that I'm feeding into the model through the dependency parser has no semantic tagging or labeling, right? So it would have nothing to distinguish those two cases other than the surrounding context in the case that you sent. So I think there is some hope. It might be one of these things where there might not be enough data. I mean, this is always an issue with Irish, that some of these things in principle should work, but if you only have 200 million words versus 200 billion words, in practice, they don't always work out the way we want.
Yeah, I just have a question there. Hi, Kevin. Seamus Langford here. I just have a question there in relation to architectures. You mentioned you were using LSTMs. Did you look at using transformer or anything like that, or would it make sense in the context of what you're trying to do?
Yes. So I mentioned LSTM. That was the 2019 work. I've experimented. So the state of the art with English on this problem is 100% transformer models, and in fact, the perspective that people take on grammar correction is just a machine translation problem, where you're literally translating from the error-full text to the error-free text. So it's a very easy machine translation problem where, like, every once in a while some word gets changed to some other word. So it's mostly copying, but you can train a transformer. And in fact, there are even variations of the transformer. I think they call them copy-based transformers or something like that, where you vary the architecture, knowing that almost all the time you're just copying source to target. But yeah, I think the transformer is the correct model for this. Again, I'm still experimenting, so I don't know what the optimal settings are going to be. But certainly the setup will be the same. You can do this in a way that depends on the existing BERT model for Irish, and then essentially just fine tune this tagging problem on top.
Okay.
Michal.
Questions?
Yeah, I just want to say, I think probably the biggest pearl of wisdom that I've taken from this is that you can take the reasons for why a token has some morphological features, such as a mutation, and you can encode it as a tag and then tag the tokens with that. That's very clever. Is that something you invented, Kevin, or was that your idea?
I guess it was my idea. I don't know. It's possible.
Yeah.
It's possible
So
somebody else has done this.
If you let your imagination run wild now, what else could you use it for? I suppose basically for anything, because every morphological feature that a token can possibly have, regardless of whether it's a grammatical number, case marking, anything, is there for a reason, right? So, and you can identify what the reason is from the semantic parts of the sentence and turn it into a tag. That's very clever.
Exactly. Yeah. That's why I'm sort of excited about this approach, is just the generality of it. Now, the hard work is the writing of the predictions, right? And it's effectively producing another rule-based system. The subtle, I mean, the thing you could ask is, why not just use that rule-based system, right? I've now essentially produced a completely new rule-based system. That I think I can answer. I think there it's the same issue, just with the brittleness and so on. You're producing kind of noisy synthetic training data using the rule-based system, training a neural network. That resulting neural network is actually much better, right? It can has some hope of solving the problem that Quivine raised. These other kind of subtleties around kind of character level issues and so on. You can learn generalizations to words and so on that it's never seen before. So all these things that would essentially be hopeless in a purely rule-based way. But yeah, it's completely general, cross-linguistically as well.
You should give it a name, this method. You should give it some sort of a catchy name so we can identify it and talk about it.
Yeah, Grammatical is not the most inspired name. That's from Edil. That's the word for what's now Gramadach in modern Irish. I wanted something that was kind of across the three Gaelic languages in any case.
Yeah, and it was probably pronounced Gramadach in medieval Irish also. So
yeah, right.
For Scottish Gaelic, I guess you know about Richard Cox's misnamed grammar in the Gaelic. It's not short, 400 pages. That's the equivalent of the Cardamom for Scottish Gaelic. For Manx, there might be bother because Chris Lewin, the main expert, I think he said that there isn't even verbal nouns. He thinks they're verbs in Manx, which, yeah, it's a big mismatch.
Yeah, so that's a place where I think all of us with the Celtic languages have kind of followed Teresa's lead, and I know there's some. I've heard from various people there's some disagreement about the way things look in both Manx and in Irish as well. So Doris has worked on some a tree bank or kind of pre-standard older texts, and there are some things that don't look right linguistically. So I should probably talk to Chris. I did the Manx one, not having any particular expertise in Manx, but my decisions in terms of part of speech tags and dependency relations were to completely follow Teresa's lead, sort of under the guise of universal dependencies being cross-linguistic.
Mm-hmm.
Yeah, verbal nouns, they are sort of halfway in between, right? They have things that they make it look like verbs in some ways and nouns in others. So.
They're very resistant to abandoning verbal nouns even in Manx, but Manx is difficult.
Question from Owen?
Sorry.
Yeah, hi Kevin, Owen here. Just a quick question. Would this approach also be useful then for sort of named recognition or named entities, or like words that are left in English to stop these causing any false positives in the grammar checker?
No, this is a good question, and in practice, when you actually start to evaluate these things, real Irish texts have lots of English embedded in them, and proper names and so on. Teresa was careful to label most of those, so there are annotations. So universal dependencies has a feature, a foreign feature. So there's a way of marking some words as not Irish. And of course, the official standard has rules that say foreign words don't get mutated in the same way that Irish words do, and so on. There is hope that because Teresa's tree bank was disciplined in the way that it handles those, that this approach could figure all of that out. I don't think it's going to be perfect, but at least the kind of annotation framework of universal dependencies kind of supports doing that. There's also, I think Teresa has named entities explicitly labeled in her tree bank as a separate. It's not part of universal dependencies officially, but there's an additional column where you can, like an auxiliary column. And I think she has the named entities marked there. So when you train the dependency parser, it's able to learn. It learns how to predict the features and the part of speech tags and all of the other stuff. So it can learn that as well in principle.
Okay, fantastic. It looks pretty amazing anyway. Thanks.
Thank you.
Willing Gesht, Ella, nog wel? Okay, I should probably have told the latecomers that we usually record these sessions. So if anyone is not happy appearing on YouTube, sorry, Kevin, I think you will. But if someone who asked a question is not comfortable with appearing in a recorded video, then let me know. But otherwise, we'll make sure to post this recording online also for people who missed it. So, Cardamom Magat, Cuivin, thanks very much. It was very interesting and very interesting follow-up questions. In May, we will have another seminar focusing on, I believe, Middle English. Was it Old or Middle English? I forgot now. So a different language, different methods. But I hope to see many of you then, and we'll send out we'll do the PR. The PR machine will start soon again. So thanks all for joining, and I hope to see many of you very soon. So. Slán go fóill go mí mar.
Thank you very much. See you later.